Okay. In order for me to evaluate you on your ability to do ray diagrams and to do the mirror equation, I'm going to give you an assignment in a moment where it asks you to draw a scale ray diagram and then use the equations that I taught you in order to solve for locations. So what we're going to do is we're going to draw a ray diagram, and then we're going to do the math, and we're going to see whether the diagrams are good or whether the equations are better. And you're going to find that the equations are better. The equations give us the answer of where we're going to find these things. So, and just to show you what the assignment looks like, it looks exactly like this. So if I go to our PowerPoint here, and I go to today's date, and I move up here to the curved mirrors, and here's the mirror equation and ray diagrams assignment. And so if I open that up, of course the internet is screaming fast all of a sudden. Actually, it's painfully slow. Maybe it's my computer. So here's, oh, wait a minute, mirror equation practice. If a converging mirror has a, yes. Yeah, no, this is what I want. And some of them have a line on it. That's right. Some of them don't have the line. You can draw your own principal axis. Oh, here it comes. It's just painfully slow. That's exciting. So I'm asking you, right, if we've got a converging mirror and we've got a DO of that and the focal length is that, and find the DI and the M using the scale diagram. And then we're asking you to find the same thing using the equations, and then in the end, C, describe the image. And you'll notice there's 1, 2, I believe there's 3 and 4. Again, the computer is really struggling. I think it's because I'm recording. And so there's 1, 2, and 3, and 4. And you can either do it on the page, or you can just do it on a separate piece of paper. It doesn't make any difference. But what I'm doing right now is, if I can get the computer to behave, everything's running pretty slowly. What I'm doing right now is I'm essentially showing you how to do a scale diagram. All right? Okay? All right. So I'm going to switch again, as per normal, over to we don't have that down yet? Oh my goodness gracious. All right. It's not allowing me to switch back.
Okay.
All right, excellent. It's good. Yep. Julian is trying to sabotage my lesson with stops and starts. All right. So I'm going to need, well, actually, I've got it on the screen in front of me. It asks, and you've got it written down, draw a scale diagram to locate the image if a 5 centimeter tall object is placed 10 centimeters in front of a concave mirror with a focal length of 5 centimeters. All right? Now, this is where we've got to draw our scale diagram, and there's a little trick to this. Everybody's gathering up equipment. As per normal, I'm going to draw a principal axis. All right? PA. And I've been trying to think about the best way to do this because there's an issue with the curvature of our protractor. And the issue is the curvature of this is designed, well, it's not designed, but it's set that we have a C of exactly, right, 5 and an F of 2.5, right? And if we can get our scale to work with the protractor, then it'll work out nicely. So notice it says that we have an object that's 5 centimeters tall and it's placed 20 centimeters in front of a concave mirror. And if I use 20 centimeters here, you'll notice that's going to drive right off the page. 20 centimeters is going to be too big. And notice that it says that we want a focal length of 5 centimeters. But for our protractor, the focal length is 2.5 centimeters. So if we have a scale of 2 to 1, right, where each centimeter represents 2 centimeters, then that's going to work out nicely for us. Everybody kind of see what I'm talking about? I'll do a little bit of math to show you. So again, I'm going to draw my mirror just like I have in the past, right? I'm going to draw the mirror like that. All right? And I'm going to put that C right there, just like I always have, because I have to. I have to put the C for what the protractor is, which means I'm going to put the F at halfway, 2.5, F. All right? Okay? Now, we need a scale for this, because F is supposed to be 5 centimeters. Right? Yep. Yep. On our diagram, what is the F on our diagram that we just drew? Yep. 2.5 centimeters. So what's our scale for this picture? Yep. 2 to 1. 2 to 1. So you see how I came up with the scale? And my second number always has to be 2.5 centimeters because I'm going to be using this protractor to draw my pictures. And that's what's going to define the scale, what the focus is that they give us compared to our 2.5 centimeters. Now we can put the rest of the picture together. We're going to put our object 20 centimeters in front. So because our scale is 2 to 1, how far away is my object going to go? 10 centimeters. And I want a 5 centimeter tall object. So how tall will the object be, Shane? Sorry? 2.5. I think we're getting the idea. I hope. That's good if we are. 2.5. That's pretty big compared to what we're used to drawing here. And there is our object. And now we draw our rays to locate this particular thing. So I'm going to start with a ray that's parallel to the principal axis. And you'll notice it's nice that I'm working on graph paper. I can even get some graph paper out if you want to take some graph paper to do the assignment on if you'd like. Where does that ray go? A ray parallel to the principal axis. Yep, through F. And what other ray would you like to use? It doesn't matter which one. I'll take a suggestion from somebody. Where would you like our second ray to go? Through F? A ray through F? How does it emerge? Parallel? Again, where the two rays come out, that's going to be the top of my arrow. And it is going to come down and touch the principal axis. And there is my eye. Okay? So now let's write all down the information about this. F was 5 centimeters. I'm just making a list of stuff. DO was, what was that distance to the DO? From mirror to object that we started with. I'm just making a list of all the variables. It was 10, but with our scale it was 20 centimeters. So what's the DI? So now we have to use our ruler out to the image. It looks like I've got 3 centimeters. Anybody else getting about 3 centimeters? We like it? Yeah. 3 centimeters. All right? Yep. Oh, nice job. Forgot about the scale. Ooh, that's really important. That's the whole purpose of doing this. 6 centimeters. Nice catch. Now we need an H. I guess we could write down the HO. How tall was that object? Yeah, it was 5, and then we shrank it down to 2.5, so 5 centimeters. So what's the HI? Well, that we have to physically measure, right? Because we did our scale diagram. I have, oh my goodness. What am I reading there? 0.8, 0.85, 0.9. It's whatever you're measuring. 9, put whatever you're measuring. Now, what do we have to do with that number? Double it. So if you've got 0.8, you're writing a 1.6. If you've got a 0.9, right, you're writing a 1.8, 1.9. Am I doing that math right? 1.8. I'll just put 1.8. I really have no particular choice. 1.8 centimeters. So what's that going to make the M? We have to calculate that. We're going to be calculating it using our HI over HO. HI over HO. What is HI? 1.8. Oh, you know what we need to put in front of that 1.8? We need a negative. We need a negative. So negative 1.8 over 5. And what do we get? Yep. 0. And it trailed off. I lost it. 34. Negative 0.34. And if you've got something other than 1.8, you got something slightly different. Okay? So that's the way the scale diagram is going to work. Now let's use the equations. So 1 over F equals 1 over di plus 1 over dou. And we're just doing exactly the same as we did for that little practice that we just did. What was the F here in this one? 1 over 5 is 1 over, and remember, we don't want the scale number, we want the real number, so I'm looking here, 1 over 20, right, DO? Oh, I've got it backwards. We want to find DI, right? 1 over DI plus 1 over 20. Am I screwing something up? Yeah, I could be. I make lots of mistakes in a day. Is that looking good? I'm not wanting what I've put on the drawing as a distance. I want what the actual numbers are. So 1 over 5.0 minus 1 over 20 equals 1 over di. And this is where we use our inverse button. 5 inverse minus 20 inverse equals, and that's after you did the inverse again. So you got a DI of 6.6, correct? 6 point, it would round to 6.7, I assume. 6.7 centimeters. So notice, look at our scale diagram. Not that great. We got 6. Should have been, it actually is, the equation is a better way of doing it. I guess not bad. So then let's calculate the M. Again, we can get the M from the DI over DO. Negative DI over DO. Or is it HI? Is it HO over, or is it DO over DI? Is it di over dou? Okay, good. You guys worked on it much more than I did on the weekend. Way to go. Good work. So negative, what was our DI? 6.7, what was the DO? 20? 20? And what do we get for an M? 6.7 divided by 20. 0.3 with a negative in front, right? 0.33. And what do we get there? Oh, look at that, 0.34. That worked out pretty good. What's the matter, Jillian? The world moves fast for Jillian. All right. And then M equals high over ho, right? And so what do we have? a negative 0.33 equals HI over, what was it, HO? 5? So HI is equal to 0.33 times 5. No one wants to share? Sorry? Negative 1.65 centimeters. What's that? You might have had a different number, or no, this should be pretty close. 1.65, 1.67. It could be that an extra decimal was carried in through here. You left a whole bunch of 0.33333. That would make yours a little more correct. Don't worry about it. We're all on the same page. I'm not worried about those little things. Okay, and there you can see how'd we do. Negative 1.8, negative 1.65, not bad. Okay? I'm looking at the time. I do want to have enough time to go outside and show you some stuff because we do have a sunny day. There is a second example. I'm not going to do the entire second example, but I am going to help you figure out what scale we want to use. So I'm not going to do the whole thing, but I am going to just talk about scale for that second example. So the second example, all right, and I'll just bring it up on the screen here, and I know I've got to switch this. So I'm going to switch the input. No, don't write this second example down. I'm just going to help you with the scale. So notice here, draw a scale diagram to locate an image if a 15 centimeter tall object is placed 15 centimeters in front of a concave mirror with a focal length of 20 centimeters. So for my scale, if you're using a protractor like we've been using that has that radius of 5 centimeters, then what must equal 5 centimeters in this example in order for us to get a good scale diagram? What is equal to 5 centimeters? Yep. Yeah, and what is that? What is it in this example? What's the focal length? You're doing too much math. 20 is the 5, so the scale is 4 to 1. Do you see what I mean? So, because it says the focal length is 20, you're going to say F is equal to 20 centimeters. The computer's really choking. You can tell the way that's working. And that's got to be equal to our 5 centimeters. And therefore, our scale is 4 to 1. All right? Everybody kind of seeing that? And then you'll squeeze all those others. So in order to get our distance of the image, I got to divide that by 4, right? And then I'm going to put that number into the picture, right? Yep. No, it doesn't. Just squeeze it into your scale. Make it fit on the scale.
So, scale always has to be 5?
Your second focal length is always 5 because that's dependent on your protractor being what you're going to use to draw your diagram. So the focal length 20 must correspond to a length of 5. Yes? Oh my goodness. You're right. I did that wrong. Did I do it wrong for the entire example too? No, it was 2.5 on the last one. So I got to fix this. Good catch. So this is 2.5. Correct. What does that make my scale then? Yep. It's 8 to 1, right? Because I'm going to divide this by 2.5 and I'm going to divide that by 2.5. So it becomes 8 to 1. 8 to 1. Good catch. Good catch. I was busy thinking about other things. So the focal length is 2.5 because that's our little one. Okay, I'm going to stop the recording there and then I'm going to get ready to start a new recording. But this shouldn't take long, but the computer's really choking. Look at this action. No, I do have to write something down.